The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
So we're ready to begin the fifth lecture. I'm glad to be back. Thank you for entertaining my colleague Haynes Miller. So today we're going to continue where he started. Namely, what he talked about was the chain rule, which is probably the most powerful technique for extending the kinds of functions that you can differentiate. Now we're going to use the chain rule in some rather clever algebraic ways today. So the topic for today is what's known as implicit differentiation. So implicit differentiation is a technique that allows you to differentiate a lot of functions you didn't even know how to find before. And it's a technique, let's wait for a few people to sit down here. Physics, huh? Okay. Well, more physics. We'll take a break. You can get those after class. All right. So we're talking about implicit differentiation, and I'm going to illustrate it by several examples. So this is one of the most important and basic formulas that we've already learned part way, namely the derivative of x to a power is a times x to the a minus 1. Now what we've done so far, what we've got so far is the exponents 0, plus or minus 1, plus or minus 2, etc. You did the positive integer powers in the first lecture, and then yesterday Professor Miller told you about the negative powers. So what we're going to do right now, today, is we're going to consider the exponents which are rational numbers, ratios of integers. So a is m over n, m and n are integers. All right, so that's our goal for right now, and we're going to use this method of implicit differentiation. In particular, it's important to realize that this covers the case m equals 1, and those are the nth roots. So when we take the 1 over n power, we're going to cover that right now, along with many other examples. Okay? So this is our first example. So how do we get started? Well, we just write down a formula for the function. The function is y is equal to x to the power m over n. That's what we're trying to deal with. And now there's really only two steps. The first step is to take this equation to the nth power. So write it as y to the n is equal to x to the m. All right, so that's just the same equation rewritten. And now what we're going to do is we're going to differentiate. So we're going to apply d by dx to the equation. Now, why is it that we can apply it to the second equation, not the first equation? So maybe I should call these equations 1 and equation 2. The point is that we can apply it to equation 2. Now, the reason is that we don't know how to differentiate x to the m over n. That's something we just don't know yet. But we do know how to differentiate integer powers. Those are the things that we took care of before. So now we're in shape to be able to do the differentiation. So I'm going to write it out explicitly over here without carrying it out just yet. That's d by dx of y to the n is equal to d by dx of x to the m power. And now you see this expression here requires us to do something we couldn't do before yesterday, namely this y is a function of x. So we have to apply the chain rule here. So this is the same as, this is by the chain rule now, d by dy of y to the n times dy dx. And then on the right-hand side, we can just carry it out. We know the formula. It's mx to the m minus 1. All right, so this is our scheme. And now you'll see in a minute why we win with this. So first of all, there are two factors here. One of them is unknown. In fact, it's what we're looking for. But the other one is going to be a known quantity because we know how to differentiate y to the n with respect to y. That's the same formula, although the letter has been changed. And so this is the same as, I'll write it underneath here, n y to the n minus 1 dy dx is equal to m x to the m minus 1. Okay, now comes, if you like, the non-calculus part of the problem. Remember, the non-calculus part of the problem is always the messier part of the problem. So we want to figure out this formula. This formula, the answer over here, which maybe I'll put in a box now, has this expressed much more simply, only in terms of x. And what we have to do now is to solve for dy dx using algebra and then solve in all the way in terms of x. So first of all, we solve for dy dx. So I do that by dividing the factor on the left-hand side. So I get here m x to the m minus 1 divided by n y to the n minus 1. And now I'm going to plug in. So I'll write this as m over n. This is x to the m minus 1. And now over here, I'm going to put in for y x to the m over n times n minus 1. All right? So now we're almost done. But unfortunately, we have this mess of exponents that we have to work out. I'm going to write it one more time. So I already recognize the factor a out front. That's not going to be a problem for me, and that's what I'm aiming for here. But now I have to encode all of these powers, so let's just write it out. It's m minus 1, and then it's minus the quantity n minus 1 times m over n. All right, so that's the law of exponents applied to this ratio here. And then we'll do the arithmetic maybe just over here in the next board. So we have here m minus 1 minus n minus 1 m over n is equal to m minus 1. And if I multiply n by this, I get minus m. And if the second factor is a minus, that's a plus. And so it's plus m over n. So altogether, the two m's cancel. And I have here minus 1 plus m over n. And lo and behold, that's the same thing as a minus 1. Just what we wanted. All right, so this equals a x to the a minus 1. Again, just a bunch of arithmetic. From this point forward, from this substitution on, it's just the arithmetic of exponents. All right, so we've done our first example here. And I guess I want to give you a couple more examples. So let's just continue. The next example, I'll keep it relatively simple. So we have example 2, which is going to be the function x squared plus y squared is equal to 1. Well, that's not really a function. This, again, is a way of defining y as a function of x implicitly. There's the idea that I could solve for y if I wanted to. And indeed, let's do that. So if you solve for y here, what happens is you get y squared is equal to 1 minus x squared, and y is equal to plus or minus square root of 1 minus x squared. So this, if you like, is the implicit definition. And here is the explicit function y as a function of x. And now, just for my own convenience, I'm just going to take the positive branch, right? This is the function. Let's just draw it right above here, right? It's really a circle in disguise, and I'm just going to take the top part of the circle. So we'll take that top hump here. All right, so that means I'm erasing this minus sign. I'm just taking the positive branch. Just for my convenience, I could do it just as well with the negative branch. All right, so now I've taken the solution and I can differentiate this. So rather than using this dy by dx notation over here, I'm going to switch notations on over here because it's less writing, and I'm going to write y prime and change notations. Okay, so I want to take the derivative of this. Well, this is a somewhat complicated function here. It's the square root of 1 minus x squared. And the right way always to look at functions like this is to rewrite them using the fractional power notation. All right? That's the first step in computing a derivative of a square root. And then the second step here is what? Somebody want to tell me? What? Chain rule. Yeah, that's good. Chain rule, that's it. So we have two things. We start with one, and then we do something else to it. So whenever we do two things to something, we need to apply the chain rule. So 1 minus x squared, square root. All right, so how do we do that? Well, the first factor I claim is the derivative of this thing. So this is a half blah to the minus 1/2. So I'm doing this by the sort of advanced method now because we've already graduated. You already did the chain rule last time. So what does this mean? This is an abbreviation for the derivative with respect to blah of blah to the 1/2, whatever it is. All right, so that's the first factor that we're going to use. Rather than actually write out a variable for it, and pass through, as I did previously with this y and x variable here, I'm just going to skip that step, and I'm going to let you imagine it as being a placeholder for that variable. So this variable is now parenthesis. And then I have to multiply that by the rate of change of what's inside with respect to x, and that is going to be minus 2x. All right, the derivative of 1 minus x squared is minus 2x. And now, again, we're glomming everything together here. We couldn't have done this example 2 before example 1 because we needed to know that the power rule worked not just for a integer, but also for a equals 1/2. We're using the case a equals 1/2 right here. It's 1/2 times, and this minus 1/2 here is a minus 1, right? So this is the case a equals 1/2, a minus 1 happens to be minus 1/2. Okay, so I'm putting all of those things together, and within a week you have to be doing this very automatically. So we're going to do it at this speed now. You want to do it even faster ultimately. Yes?
Could you have done it implicitly without
the question is, could I have done it implicitly without the square roots? And the answer is yes, that's what I'm about to do. Okay? So this is an illustration of what's called the explicit solution. So this guy is what's called explicit. And I want to contrast it with the method that we're going to now use today. So it involves a lot of complications. It involves the chain rule, and as we'll see, it can get messier and messier. And then there's the implicit method, which I claim is easier. All right? So let's see what happens if you do it implicitly. The implicit method involves, instead of writing the function in this relatively complicated way with the square root, it involves leaving it alone. Don't do anything to it. In this previous case, we were left with something which was complicated, say x to the 1/3 or x to the 1/2 or something complicated, we had to simplify it. We had an equation 1 which was more complicated. We simplified it and then differentiated it. And so that was the simpler case. Well, here the simplest equation for us to differentiate is the one we started with, because squares are practically the easiest things after first powers or maybe 0th powers to differentiate. So we're leaving it alone. This is the simplest possible form for it. And now we're going to differentiate. So what happens? So again, what's the method? Let me remind you. You're applying d by dx to the equation. So you have to differentiate the left side of the equation and differentiate the right side of the equation. So it's this. And what you get is 2x plus 2y y prime is equal to what? 0. Derivative of 1 is 0. All right, so this is the chain rule. Again, I did it a different way. I'm trying to get you used to many different notations at once here. Well, really just two, just the prime notation and the dy dx notation. And this is what I get. All right? So now, all I have to do is solve for y prime. So that y prime, if I put the 2x on the other side, is minus 2x and then divide by 2y, which is minus x over y. All right? So let's compare our solutions. I apologize, I'm going to have to erase something to do that. So let's compare our two solutions. I'm going to put this underneath and simplify it. So what was our solution over here? It was a half 1 minus x squared to the minus a half times minus 2x. That was what we got over here. And that is the same thing if I cancel the 2's and I change it back to looking like a square root. That's the same thing as minus x divided by square root of 1 minus x squared. All right, so this is the formula for the derivative when I do it the explicit way. And I'll just compare them, these two expressions here. And notice that they are the same. All right, they're the same because y is equal to square root of 1 minus x squared. Yeah, question.
Bottom half of the circle.
The question is, why did the implicit method not give the bottom half of the circle? Very good question. The answer to that is that it did. I just didn't mention it. Well, wait, I'll explain. So suppose I'd stuck in a minus sign here. Okay? I would have gotten this with with an extra minus sign. But then, when I compared it to what was over there, I would have had to have another different minus sign over here. So actually, both places would get an extra minus sign, and they would still coincide. So actually, the implicit method is a little better. It doesn't even notice the difference between the branches. It does the job on both the top and the bottom half. Another way of saying that is that you're calculating the slopes here. So let's look at this picture. Here's a slope. Let's just take a look at a positive value of x and just check the signs to see what's happening. If you take a positive value of x over here, x is positive, this denominator is positive, the slope is negative. You can see that it's tilting down. All right? So it's okay. Now, on the bottom side, it's going to be tilting up. And similarly, what's happening up here is that both x and y are positive, and this x and this y are positive, and the slope is negative. On the other hand, on the bottom side, x is still positive, but y is negative, and it's tilting up because the denominator is negative, the numerator is positive, and this minus sign makes it a positive slope. So it matches perfectly in every category. So this is complicated, however, and it's easier just to keep track of one branch at a time, even in advanced math. Okay? So we only do it one branch at a time. Other questions? Okay, so now I want to give you a slightly more complicated example here. And indeed, some of the, so here's here's a little more complicated example. It's not going to be the most complicated example, but, you know, it'll be a little bit tricky. Okay? So this example, I'm going to give you a fourth order equation. So y to the fourth plus xy squared minus 2 is equal to 0. Right? Now, it just so happens that there's a trick to solving this equation. So actually, you can do both the explicit method and the non-explicit method. Okay? So the explicit method would say, okay, well, I want to solve for this. So I'm going to use the quadratic formula, but on y squared. This is quadratic in y squared, because there's a fourth power and a second power, and the first and the third powers are missing. So this is y squared is equal to minus x plus or minus the square root of x squared minus 4 times minus 2 divided by 2. Okay, so this x is the b, this minus 2 is the c, and a is equal to 1 in the quadratic formula. And so the formula for y is plus or minus the square root of minus x plus or minus the square root of x squared plus 8 divided by 2. All right? So now you can see this problem of branches. This happens actually in a lot of cases, coming up in an elaborate way. You have two choices for the sign here. You have two choices for the sign here. Conceivably, there are as many as 4 roots to this equation because it's a fourth degree equation. It's quite a mess. You should have to check each branch separately. And this really is that level of complexity. And in general, it's very difficult to figure out the formulas for quartic equations. But fortunately, we're never going to use them. That is, we're never going to need those formulas. So the implicit method is far easier. So the implicit method just says, OK, I'll leave the equation in its simplest form and now differentiate. So when I differentiate, I get 4y cubed y prime plus, now here I have to apply the product rule. So I differentiate the x and the y squared separately. First, I differentiate with respect to x, so I get y squared. Then I differentiate with respect to the other factor, the y squared factor, and I get x times 2y y prime. And then the 0 gives me 0, so minus 0 equals 0. All right, so there's the implicit differentiation step. And now I just want to solve for y prime. So I'm going to factor out 4y cubed plus 2xy. That's the factor on y prime. And I'm going to put the y squared on the other side, minus y squared over here. And so the formula for y prime is minus y squared divided by 4y cubed plus 2xy. So that's the formula for the solution, for the slope. Do you have a question?
For the y, would we have to put in what you solved for explicit?
So the question is, for the y, would we have to put in what we solved for in the explicit equation? And the answer is absolutely yes. That's exactly the point. So this is not a complete solution to a problem. We started with an implicit equation, we differentiated, and we got, in the end, also an implicit equation. It doesn't tell us what y is as a function of x. We have to go back to this formula to get the formula for x. So for example, well, let me give you an example here. So this is the hides a degree of complexity of the problem, but it's a degree of complexity that we must live with here. So for example, at x equals 1, you can see that y equals 1 solves. That happens to be, solves y to the 4th plus xy squared minus 2 is equal to 0. That's why I picked the 2, actually. So it would be 1 plus 1 minus 2 equals 0. I just wanted to have a convenient solution there to pull out of my hat at this point. So I did that. And so we now know that when x equals 1, y equals 1, so at 1, 1 along the curve, the slope is equal to what? Well, I have to plug in here minus 1 squared divided by 4 times 1 cubed plus 2 times 1 times 1. That's just plugging in that formula over there, which turns out to be minus 1/6. All right, so I can get it. On the other hand, but at, say, x equals 2, we're stuck using this formula star here to find y. Okay? Now, so let me just make 2 points about this, which are just philosophical points for you right now. The first is, when I promised you at the beginning of this class that we were going to be able to differentiate any function you know, I meant it very literally. What I meant is, if you know the function, we'll be able to give a formula for the derivative. If you don't know how to find the function, you'll have a lot of trouble finding the derivative. So we didn't make any promises that if you can't find the function, you will be able to find the derivative by some magic. That will never happen. And however complex the function is, a root of a 4th degree polynomial can be a pretty complicated function of the coefficients. We're stuck with this degree of complexity in the problem. But the big advantage of this method, notice, is that although we've had to find star, we had to find this formula star, and there are many other ways of doing these things numerically, by the way, which we'll learn later. So there's a good method for doing it numerically. Although we had to find star, we never had to differentiate it. We had a fast way of getting the slope. So we needed to know what x and y were, but y prime we got by an algebraic formula in terms of the values here. So this is very fast for getting the slope once you know the point. Yes?
What's in the parentheses? But at
What's in the parentheses? Sorry, this is, well, let's see if I can manage. Is this little, is this the parentheses you're talking about? Ah, say. Oh, this says say. Well, so maybe I should put commas around it, but it was S-A-Y, comma, comma. Okay? Well, here was at x equals 1, and here's but at, say, I'm just throwing out a value here. Any other value. Actually, there is one value, my favorite value. Well, this is easy to evaluate, right? X equals 0. I can do it there. That's maybe the only one which is, the others are a nuisance. Okay. All right. Other questions? Okay, now we have to do something more here. So I claimed to you that we could differentiate all the functions we know, but really we can learn a tremendous about some functions which are really hard to get at. So this implicit differentiation method has one very, very important application. To finding inverse functions, or finding derivatives of inverse functions. So let's talk about that next. So first, maybe we'll just illustrate by an example. If you have the function y is equal to square root x for x positive, then, of course, this idea is that we should simplify this equation, and we should square it. So we get this somewhat simpler equation here. And then we have a notation for this. If we call f of x equal to square root of x, and g of y is equal to x, this is the reversal of this, then the formula for g of y is that it should be y squared. And in general, if we start with any old y is equal to f of x, and we just write down this is the defining relation for a function g, the property that we're saying is that g of f of x has got to bring us back to x. And we write that in a couple of different ways. We call g the inverse of f, and also we call f the inverse of g. Although I'm going to be silent about which variable I want to use because people mix them up a little bit, as we'll be doing when we draw a few pictures of this. So let's draw a picture of both f and f inverse on the same graph. So first of all, I'm going to draw the graph of f of x is equal to square root of x. All right, that's some shape like this. And now, in order to understand what g of y is, so let's do the analysis in general, but then we'll draw it in this particular case. If you have g of y is equal to x, that's really just the same equation, right? This is the equation g of y is equal to x. That's y squared equals x. This is y equals square root of x. Those are the same equation. It's the same curve. But suppose now that we wanted to write down what g of x is. Okay, in other words, we wanted to switch the variables, so draw them, as I said, on the same graph with the same x and the same y axes. Then that would be, in effect, trading the roles of x and y. We have to rename every point on the graph, which is the ordered pair xy, and trade it for the opposite ones. And when you exchange x and y, so to do this, exchange x and y. And when you do that, graphically, what that looks like is the following. Suppose you have a place here, and this is the x and this is the y. Then you want to trade them. So you want the y here, right, and the x up there. So it's this sort of opposite place over there. And that is the place which is directly opposite this point across the diagonal line x equals y. So you reflect across this, or you flip across that, and you get this other shape that looks like this. Maybe I'll draw it with a colored piece of chalk here. All right. So this guy here is y equals f inverse of x, right? And indeed, if you look at these graphs, this one is the square root. This one happens to be y equals x squared. Right? They're just, it's if you take this one and you turn it and you reverse the roles of the x-axis and the y-axis and tilt it on its side. All right, so that's a picture of what an inverse function is. And now I want to show you that the method of implicit differentiation allows us to compute the derivatives of inverse functions. So let me just say it in general, and then I'll carry it out in particular. So implicit differentiation allows us to find the derivative of any inverse function provided we know the derivative of the function. All right? So let's do that for what is an example which is truly complicated and a little subtle here and has a very pretty answer. So we'll carry out an example here, which is the function y is equal to the inverse tangent. So again, for the inverse tangent, all of the things that we're going to do are going to be based on simplifying this equation by taking the tangent of both sides. So let me remind you, by the way, the inverse tangent is what's also known as arctangent of x. That's just another notation for the same thing. And the way what we're going to use to describe this function is the equation tan y is equal to x. That's what happens when you take the tangent of this function. So this is how we're going to figure out what the function looks like. All right, so first of all, I want to draw it, and then we'll do the computation. Okay, so let's make the diagram first, make the sketch. So I want to do something which is analogous to what I did over here with the square root function. So first of all, I remind you that the tangent function is defined between two values here, which are pi over 2 and minus pi over 2. And it starts out at minus infinity and curves up like this. So that's the function tan x. Okay? And so the one that we have to sketch is this one which we get by reflecting this across the axis. All right? So that's going to be, well, not the axis, sorry, the diagonal. All right? This slope, by the way, should be less, so a little lower here so that we can have it going down and up. All right, so let me show you what it looks like. So on the front end, it's going to look a lot like this one. So this one had curved down, and so the reflection across the diagonal curved up. Here, this is curving up, so the reflection is going to curve down. It's going to look like this. All right, maybe I should, sorry, let's use a different color because it's reversed from what we had before. So I'll just call it green. All right, we'll do this. All right, now the original curve in the first quadrant eventually had an asymptote which was straight up. So this one is going to have an asymptote which is horizontal, and that level is what? What's the highest? Right there. It's this pi over 2 up here. All right? Now, similarly, the other way, we're going to do this. And this bottom level is going to be minus pi over 2. So there's the picture of this function. It's defined for all x. So this green guy is y equals tan inverse x. And it's defined all the way from minus infinity to infinity. And to use a notation that we had from limit notation, as x goes to infinity, let's say, tan inverse x is equal to pi over 2. That's an example of one value that's of interest in addition to the finite values. Okay, so now the first ingredient that we're going to need is we're going to need the derivative of the tangent function. So I'm going to recall for you, and you maybe haven't worked this out yet, but I hope that many of you have, that if you take the derivative with respect to y of tan y, so this you do by the quotient rule. So this is of the form u over v, right? You use the quotient rule. So I'm going to skip this. Okay. But what you get in the end is some marvelous simplification. It comes out to be cosine squared y. Here, 1 over cosine squared. You can recognize the cosine squared from the fact that you should get v squared in the denominator. And somehow the numerator all cancels and simplifies to 1. Okay? And this is also known as secant squared y. All right? So that's something that, if you haven't done it yet, you're going to have to do this as an exercise. All right. Okay, so we need that ingredient, and now we're just going to differentiate our equation. And what do we get? We get, again, d by dy tan y times dy dx is equal to 1. Or, if you like, 1 over cosine squared y times, in the other notation, y prime is equal to 1. So I've just used the formula that I just wrote down there. All right, now all I have to do is solve for y prime. It's cosine squared y. Okay? Unfortunately, this is not the form that we ever want to leave these things in. Again, this is the same problem we had with that ugly square root expression or with any of the others. We want to rewrite it in terms of x. Our original question was, what is d by dx of tan inverse of x? Now, so far, we have the following answer to that question. It's cosine squared of tan inverse x. Okay? Now, this is a correct answer, but way too complicated. Now, that doesn't mean that if you took a random collection of functions, you wouldn't end up with something this complicated. But these particular functions, these beautiful circular functions involved with trigonometry, all have very nice formulas associated with them. And this simplifies tremendously. And so one of the skills that you need to do to develop when you're dealing with trig functions is to simplify this. And so let's see now that expressions like this all simplify. So here we go. There's only one formula, one ingredient that we need to use to do this, and then we're going to draw a diagram. So the ingredient, again, is the original defining relationship that tan y is equal to x. So tan y equals x can be encoded in a right triangle in the following way. Here's the right triangle, and tan y means that y should be represented as an angle. And then its tangent is the ratio of this vertical to this horizontal side. So I'm just going to pick two values that work, namely x and 1. Those are the simplest ones. So I've encoded this equation in this picture. And now, all I have to do is figure out what the cosine of y is in this right triangle here. In order to do that, I need to figure out what the hypotenuse is. But that's just square root of 1 plus x squared. And now I can read off what the cosine of y is. So the cosine of y is 1 divided by the hypotenuse. So it's 1 over square root, 1 plus x squared. That's it. Yeah. Okay? And so cosine squared is just 1 over 1 plus x squared. And so our answer over here, the preferred answer, which is way simpler than what I wrote up there, is that d by dx of tan inverse x is equal to 1 over 1 plus x squared. Okay? Now, maybe I'll stop here for one more question. I have one more calculation which I can do even in less than a minute. So we have a whole minute for questions. Any questions? Yeah?
What happens to the inverse?
Say that again.
Inverse tangent.
What happens to the inverse tangent? The inverse tangent, okay, so this inverse tangent is the same as this y here. Those are the same thing. So what I did was I skipped this step here entirely. I never wrote that down, but the inverse tangent was that y. The issue was, what's a good formula for cosine y in terms of x? So I am evaluating that, but I'm doing it using the letter y. So in other words, what happened to the inverse tangent is that I called it y, which is what it's been all along. Okay, so now I'm going to do the case of the sine, the inverse sine. And I'll show you how easy this is if I don't fuss with, because this one has an easy trig identity associated with it. So if y is equal to sine inverse x, then sine y is equal to x. And now watch how simple it is when I do the differentiation. I just differentiate. I get cosine y times y prime is equal to 1. All right? And then y prime, so that implies that y prime is equal to 1 over cosine y. And now to rewrite that in terms of x, I have to just recognize that this is the same as this. Which is the same as 1 over square root of 1 minus x squared. So all told, the derivative with respect to x of the arc sine function is 1 over square root of 1 minus x squared. Right, so these implicit differentiations are very convenient. However, I warn you that you do have to be careful about the range of applicability of these things. And you have to draw a picture like this one to make sure you know where this makes sense. In other words, you have to pick a branch of the sine function to work that out. And there's something like that on your problem set, and it's also discussed in your text. So we'll stop here.